Hi class, Dr. Searcy here with the PSYC B1B Chapter 2 lecture. As you can tell, the title of the lecture is Synapses. This is something that we started talking about in Chapter 1 and that we'll continue talking about in Chapter 2. I want to go ahead and begin with a little bit of review. First thing that we're going to want to remember is that we're talking basically about neurons and them communicating with each other. Here's that diagram of a whole neuron and a half that we looked at from Chapter 1. What do we want to remember about this? First thing that we want to remember is that probably the most important part of this diagram is the synapse. Right, we said that the synapse consisted of these three parts that you're seeing in the diagram, where the first part is a terminal button. That's this part of the neuron here, where we said that neurotransmitters exit. They go into this other part called the cleft, which we said was the space between the terminal buttons of the sending neuron and the dendritic receptors of the receiving neuron. So then the last part of the synapse is the dendrite, right? And let's just remember that on the dendrite, there are these little receptors that are there to receive the neurotransmitters that have been secreted out of the terminal buttons. Okay, so with that, let's remember what we're talking about here is the neurons communicating with each other. We talked about different times during the communication last time. Let's remember that we refer to them as either the resting membrane potential or the action potential. And the thing that we said about these two potentials was that the resting membrane potential was the state of the neuron before communication, right? It was just resting. Maybe it was waiting for a signal, waiting for a neurotransmitter from a neighbor, but it was not communicating in the moment. Then we also described the action potential. Here I've got it, is after communication. I don't quite like that. I think I'd rather think of it as more what's happening during communication, right? During communication, the neuron that has received a signal from its neighbor is now firing off its own signal. Remember the way that I said that, the neuron that's received a neurotransmitter from a neighbor is now firing off its own neurotransmitter to another neighbor. In addition to that, let's also remember what the electrical charge was of the neurons during these two states. During resting membrane potential, we said that the charge was more negative inside the neuron. And then when the neuron is sending out a neurotransmitter, right, it's in action potential, then the inside is more positive. All right, so let's just write more positive inside. Okay, so in addition to that, let's also remember that for each of these potentials, we gave them a couple of AKAs. Or I think I gave an AKA to the resting membrane potential state, right? I said that it can also be referred to as polarized. If a neuron is more negative inside, it's waiting on communication, it is in a state where it is polarized. On the other hand, if now a neuron is communicating with another neuron, it's sending out a neurotransmitter, then it's become more positive inside, it's entered into a state of action potential. This can also be referred to now as the neuron being depolarized. Kind of an important pair of terms here, right? So we're saying polarized is when the inside is more negative. Depolarized is when the inside is more positive. You may notice that I've got this space over here. The reason why I've got this space over here is because it's also possible to have a third state of a charge. And that third state of a charge could be, say, where here we have the state is positive, here it's negative. This third state could be where it's even more negative, right? So we kind of have like a continuum here. Positive charge, really negative charge. If this is going to happen, what's going to happen is that the inside is just going to get more negative ions than positive ions, even more negative ions than during this state. If that happens, then this would be referred to as the cell being hyperpolarized. So here are three terms that we just kind of want to hang on to. Depolarized is when the neuron is in a state of active potential. Polarized is when the neuron is in a state of resting membrane potential. And hyperpolarized is when the neuron is really, really, really negative inside. Okay, so that's the stuff that we wanted to review. Now let's go ahead and start talking about the new stuff for this chapter. One of the first things that the chapter brings up is that oftentimes when neurons communicate with each other, they communicate inside of what are referred to as reflex arcs. A reflex arc can be defined as just a neural pathway, right? And so by neural pathway, what I mean is it could be like a collection of neurons that talk to each other, and they all like share a synapse. They all communicate some information. The pathway is that the communication is starting at the neurons, but then it's going like to the brain or to the spinal cord. So if that's the case, one thing we want to see is that this reflex arc is going to occur in the spine of the organism that we're talking about, right? So if we're talking about humans, the reflex arc is in the spinal cord of the human being. The reason why these are there is because it's supposed to make for a system that provides a more efficient communication. And I'll explain that in just a moment. But if that's the case, another thing that we want to think about is, well, okay, what specific neurons make up the reflex arc? And the answer to that question is that the reflex arc is made up of what are referred to as sensory neurons, also interneurons, and then a third type of neuron, the motor neurons. Okay. So if here we're describing a reflex arc, right, we're talking about it being this neural pathway, it's in the spinal cord, it's made up of these three different kinds of neurons. Let's take a look at this diagram that kind of illustrates what we're talking about here. First, let's just note what we have in the diagram is an arm that's connected to a hand that's touching a hot pot of water. Right, so think about your reaction, your physical reaction when you touch a hot pot of water, right? You basically, as soon as your neurons communicate to each other that the pot is hot, you have this action of taking your hand away from the pot. But how does it happen? Well, the way it happens is, to begin with, you've got these sensory neurons that are connected to the skin. They pick up the information that the pot is hot, that you probably ought to drop it because it's going to injure you. That information is sent to the interneuron, which is about right here, right? And you're seeing that this interneuron is inside this chunk of spinal cord, the central nervous system. And that interneuron is actually like a mediator or like a headquarters. It receives the information from the sensory neuron, and that information is supposed to go to the brain, right? So the brain can tell the hand to let go of the pot. However, evolutionarily speaking, it would take a long time to do that, maybe too long to do that. So the interneuron is going to act like a quick reaction headquarters. They get this message from the sensory neuron, and they react to that information by immediately telling the motor neuron to make the fingers let go of the pot, right? So this network of neurons that we're talking about here are there to communicate with each other because that provides a more efficient communication, which would lead to a quicker reaction than if you waited for the your message to get to the brain and then for the brain to send it back for you to let go of the pot. Right, so that's the reason why the reflex arc is there. That's the benefit that it serves. Now, I want to go back to introducing a couple of other terms, right? As we're talking about these neurons communicating with each other, let's also note that we're basically talking about two types of neurons, or at least two types of communicators. There's the presynaptic neurons and the postsynaptic neurons. The presynaptic are the neurons that send the communication. The postsynaptic neurons are the neurons that receive the communication, right? So for example, if we're saying that these two neurons are talking to each other because this neuron is sending a message to this neuron is the presynaptic neuron, and this neuron is the postsynaptic neuron. Okay, continuing with this idea of providing you with some necessary terminology, I now want to move on to the next point that we have to make, and that is with regard to this thing called summation. Right, so here we're talking about the neurons communicating with each other, them being, or at least beginning, in a state of resting membrane potential, and then moving to a state of action potential. The way that we move from resting membrane potential to action potential can often be described in terms of summation, where summation is a process that determines whether the action potential is elicited, right? Whether the action potential happens or not. As it turns out, it isn't the case that one neurotransmitter causes a reaction in the postsynaptic neuron. Instead, what's going to cause a reaction in the postsynaptic neuron is either temporal summation, right, where temporal summation is repeated elicitations from one neuron, or the action potential is going to be caused by spatial summation, which is simultaneous elicitations from multiple neurons. All right, so we have a diagram that basically illustrates both of these two types of summation. In this diagram, we're looking at a neuron placed next to another neuron, right? So this is our presynaptic neuron. This is our postsynaptic neuron. And you see that this neuron is about to send a message to this neuron, right? That's where this action potential is going to happen. But the way that the message is going to get sent over is through the two types of summation. The temporal summation here, where we see one receptor of a dendrite, right? So we got these dendrites right here. One receptor is being repeatedly stimulated. That's this temporal summation. On the other hand, at the bottom of the illustration, you've got a dendrite here and a dendrite there, right? So it's two different dendritic receptors being stimulated from multiple neurons. That is an example of spatial summation. The thing that you want to see with spatial summation is that here two different dendrites are being activated, but they're being activated simultaneously. They're being activated at the same time. Okay, so we're saying then that the action potential is going to occur as a result of summation, either temporal summation or spatial summation. Now, when this happens, right, this reaction occurs, we often think of the reaction as a type of graded potential, where a graded potential can be described as changes in the membrane potential, right? Either resting or action. The thing that we're saying here, though, is that we're not going to just go from resting membrane potential to action potential, but instead we could have a graded potential, where a graded potential is going to be having some reaction that's going to vary in size, as opposed to an all or nothing, right? Where an all or nothing would be the action potential. Okay, so when these graded potentials occur, there are basically two types that can happen. Either the excitatory postsynaptic potential, the EPSP for short, or the inhibitory postsynaptic potential, the IPSP for short. Now, what we want to look at with these two types of potentials, right? So these are like two types of graded potentials. We want to look at these three different things. What happens to the cell during each type of potential? What is the effect of each type of potential? And what is the membrane action that occurs? All right, so to begin with, let's point out what happens to the cell with the excitatory postsynaptic potential. Basically, what's going to happen here is that the inside of the cell is going to become depolarized. Remember that if it's depolarized, then it's going to become more positive inside. If it's going to be more positive inside, then that's going to cause an increase in activity, right? It's going to cause, let's go ahead and write it down here. It's going to cause a action potential. Okay. And the way it's going to happen is sodium is going to flow into the neuron. Remember from chapter 1, we said that sodium, right? Remember its chemical symbol was Na, and we said that it was a positively charged ion. So if it's going to flow in, that's what's going to cause the inside of the cell to become more positive, and that's what's going to lead to the action potential. So then, what is an inhibitory postsynaptic potential? Well, an inhibitory postsynaptic potential is where the cell is going to become hyperpolarized. Remember, we said that hyperpolarized is where the cell is going to become even more negative. And that's going to lead to a suppression in activity, right? So, whereas this is going to cause some reaction, this is going to suppress some type of reaction. How's it going to do it? Well, to begin with, remember, the inside of the cell is becoming more negative. And the way it's going to become more negative is either potassium is going to leave. Remember we said potassium had the chemical symbol of K, and it also carried a positive charge. So it's going to, the inside of the cell is going to become more negative by this positively charged potassium leaving the inside of the cell, or chloride entering the cell. Let's remember that we said that chloride carried a negative charge. Okay, so since we've just been talking about these graded potentials, right? And we pointed out the excitatory postsynaptic potential versus the inhibitory postsynaptic potential. I just wanted to have us take a look at this diagram that's kind of an illustration of all the different kinds of potentials that we've been talking about, right? So here we're seeing that we've got 5 different kinds of reactions. And the way that we're looking at each kind of reaction is in terms of the electrical activity that occurs with that reaction. Maybe to begin with, let's note that the line is starting right here, right? And if the line is right there, that line is indicating that there's a resting potential that's in place, right? There's a resting memory potential. It's more negative inside, and that more negative inside is where the inside of the cell is at -70. Okay, so let's say that we have this first thing that occurs, an EPSP, an excitatory postsynaptic potential. There's only one thrust here. Remember, so we're talking about the summations here. It was just one temporal summation. It doesn't have a very big effect. It does cause the cell to become more positive inside, right? It's going from a -70 to a -65, but it's not having very much of an effect. Even though it is becoming more positive, it's not positive enough to cross this threshold that's going to lead to an action potential. So then we've got this step 2, or this second type of EPSP. Here, we're seeing that there's temporal summation that's occurring, right? So one dendrite is being repeatedly stimulated. Here it got stimulated twice. When that happened, it led to a further increase in positivity inside the cell, but it still didn't cause an action potential to occur. So then in this third illustration, what's happening, we're saying that we got 3 EPSPs, right? And maybe these are now the temporal summations. But when we've moved from just 2 EPSPs to 3 EPSPs, we're seeing that that was enough to cause the inside of the cell to become so positive inside that it actually caused an action potential. Notice how quickly the action potential is occurring. It's like basically thrusts up really fast and then goes right back down to being negatively charged. So let's take a look at this fourth type of EPSP. Here we're saying, simultaneous EPSPs combine spatially to exceed the threshold, right? So here is that spatial summation, the one where we were saying that different dendrites are being stimulated at the same time. That also here is leading to an increase in positivity inside the cell, and so also causing the depolarization, the action potential. But then if we look at this fifth example of what's happening, or what could happen, we see that we get an IPSP here, inhibitory postsynaptic potential. What's happened here is that the cell got stimulated, but the direction that the stimulation occurred was the inside became even more negative than it had been before, right? Even more negative means that it's going to suppress the activity, it's going to stop anything from happening. Okay, so that's our illustration of how the EPSPs and the IPSPs can occur. Now from here, last thing that I want to talk about is I thought the book did an interesting job of describing how different types of illicit drugs act at our synapses. So what we're going to go over for the rest of this lecture is a simplified look at how drugs act at the synapses. And we'll start with the drug marijuana. Right, so I'm sure that you students are familiar with what marijuana is. I'm sure that we all have some understanding. If you've never used it, you've learned that it basically causes the user to feel a sense of relaxation, maybe a sense of euphoria, happiness, those kinds of things. So what is it about the drug? What is it about the drug that's causing that at the synapse level? Basically, the way I want to describe this section is in terms of a before and an after effect. Okay, so I'm going to start by describing what the synapse looks like before someone ingests marijuana. The thing that we're seeing here is we've got basically three actors at a synapse. In this particular synapse, we've got two sender neurons, right? We've got a neuron here that's going to be sending inhibitors out of its terminal button. An inhibitor, by the way, is going to be some neurotransmitter that's going to stop some action potential from occurring. But then you've got this second neuron here, and this neuron has a terminal button that is releasing dopamine into a synaptic cleft. The reason why it's doing it is because that dopamine molecule is going to go in the synaptic cleft to a dendritic receptor, where it's going to stimulate that dendrite of some cell or some neuron that's nearby. Okay, so normally what would happen is this dopamine activity would be regulated, right? Remember we said that dopamine is going to have the effect of causing the person to feel pleasure. So if it's coming out, it's stimulating a dendrite. The person that is at the end of all this is experiencing some pleasurable experience. But it's going to be stopped by an inhibitor naturally being secreted out and blocking the dopamine. Here, you're seeing that that's not happening, though. An inhibitor is not leaving this terminal button. And the reason why is because it is blocked. This door where inhibitors would come out is blocked by this molecule with the A in it. What does the A stand for? The A stands for anandamide. And what it does is a naturally occurring substance that the body makes. It flows into a synaptic cleft and it blocks the door which the inhibitors would come out of. Why does it do it? It blocks the inhibitors from blocking the dopamine release, right? So anandamide floats into a synaptic cleft. It blocks a door where an inhibitor is trying to get out. And as long as it's blocking that door, the inhibitor can't come out and stop the dopamine from going to a dendrite. And so that's what's causing a person to feel naturally good. Okay? But then let's say that individual gets a hold of some marijuana and decides to ingest that marijuana. What is the marijuana going to do to that individual? Basically, what's going to happen is the marijuana is now going to act exactly the same way that anandamide was acting before. The marijuana is going to float into a synaptic cleft. It's going to hunker down here at a door of an inhibitor, and it's going to block inhibitors from getting out. As it does that, the inhibitors can't get out, and so dopamine is free to flow into the cleft, go ahead and float on over to a dendritic receptor, stimulate the receptor, and cause that feeling of pleasure. Okay, so I guess the way we describe this, we would say that the marijuana acts like a super anandamide. And what I mean by a super anandamide is that the anandamide is going to block the inhibitor for a small amount of time, right? You're going to feel good and you're going to feel okay. But the anandamide is going to quickly dissolve, it's going to quickly break up so that the inhibitor can come out and block the dopamine. Marijuana, on the other hand, is stronger than anandamide. It's going to be more robust. It's going to last longer. And so it's going to do a better job of blocking inhibitors from coming out, allowing the dopamine to flow to the dendrite. And that's what then is producing that feeling of euphoria for the marijuana ingester. Okay, let's go ahead and move on to the next drug. The next drug is cocaine. Thinking that you may be less familiar with its effects. Kind of seems like cocaine is a drug that is used less commonly than marijuana is. So the effect of cocaine then is that it is thought of as a stimulant. For the person that ingests it, it causes that euphoric feeling, like a feeling of feeling good. But it also acts as a stimulant in the sense that it causes a person to feel energized, maybe even to feel confident, to feel stimulated to do something. Often you'll see this effect in like party atmospheres. A person that uses cocaine becomes more sociable, more talkative, more brave in terms of approaching strangers, less inhibited in terms of trying to get what they want, right? And that's the reason why the cocaine user chooses to use the cocaine to produce all those effects. Okay, so let's talk about what's going on with the synapse here. To begin with, let's take another look at a before situation, right? So before a cocaine user uses the cocaine, we could say that the synapse system is regulated this way, where yes, you've got a dopamine releasing terminal button that's releasing the dopamine into a synaptic cleft. That dopamine is floating over to a dendrite, right, a receptor right there, where it's going to stimulate this dendrite. But then after a while, it's going to leave that dendrite and it's going to go back to the terminal button that it came from. Remember that we described this process in chapter 1 as reuptake, right? So here we're saying that reuptake is what causes dopamine release, dopamine reaction to stop. So just one more time. The dopamine gets released by the neuron, goes across the synaptic cleft to the receptor, stimulates the receptor for a little while, but then leaves that receptor and gets taken back up into the neuron that it came from, hence reuptake. So what happens to this process when an individual ingests cocaine? Basically what's going to happen is that cocaine the molecule is going to flow into a synaptic cleft. And now it is going to block reuptake. Right? So here we're seeing the diagram again. It's the after situation. The person's ingested cocaine. That cocaine has gotten into the cleft. It's now blocking the entrance for the dopamine molecule to get back into the neuron. Because the dopamine molecule can't get back into the neuron, it's going to bind again and again to the dendritic receptor that it's been stimulating. And that's what's causing that continued feeling of exuberance, euphoria, stimulation. Okay, now let's move on to a third type of drug, methamphetamine. First, I guess we should say that in describing methamphetamine, methamphetamine is a type of amphetamine. Amphetamines are a class of drugs generally referred to as stimulants, right? Much like cocaine. But the reason why amphetamines might be used is because they have a more therapeutic effect, right? Where the stimulation can be controlled, those kinds of things. Okay, so we have another situation here where a drug user has taken a drug. This time it's methamphetamine. Its effects are going to be very similar to the effects of cocaine. Methamphetamine is also going to cause the user to feel stimulated, to feel exuberant, to feel euphoric. So it sounds like the two drugs then, because they have this, similar effects, are going to work similarly to each other. Let's see if that's actually the case. Beginning with our before situation. Let's say that this time for the before situation, we're just going to describe the before situation as where dopamine reuptake takes place again, right? We've described it up here, so we don't need to redraw it down here. Let's just note that the same process that was happening here is happening here as well. So then the methamphetamine user uses the methamphetamine, gets into their system, and how's it going to work? Well, we've got a diagram here where basically we're saying the same thing. The reuptake process is supposed to happen again, except that the way that it gets interrupted is that the methamphetamine now is going to mimic dopamine. That's important for the reuptake part, right? So what's going to happen here is now you've got methamphetamine in the synaptic cleft in addition to dopamine being in the synaptic cleft. Everything's going to get taken back up into the terminal button that it came from. But what we're saying here is that because the meth mimics the dopamine, it too is going to go back into the terminal button along with the dopamine. This is going to lead to a problem though. What's going to happen is that terminal button is going to get so filled up with these different molecules, the meth, the dopamine, that it's going to now need to kick some stuff out. What's it going to end up kicking out? It's going to end up kicking out dopamine molecules. And those dopamine molecules are then going to go back to the dendritic receptor that it was stimulating before, therefore causing that continued feeling of exuberance, euphoria, stimulation. Okay, so we've just described the effects of marijuana, cocaine, and methamphetamine. Let's continue this party and now talk about see if we can get this to focus. Heroin. Waiting for my thingy to focus here. Okay, so let's say now what's going to happen with the heroin, there we go, is that you got another before-after situation. The before situation this time, though, is where you've got those three actors, kind of like how we were talking about with the marijuana, right? So you got the dopamine terminal button that's letting dopamine into the synaptic cleft. That dopamine molecule is then going to go to a dendritic receptor and it's going to stimulate it. However, this activity is going to be regulated by some inhibitor, releasing some inhibitor neurotransmitter that's going to block the release of the dopamine. Here we're seeing that before someone ingests heroin, there's this other natural substance that's now going to block the inhibitor. This natural substance is a natural opiate, right? So like a pain reliever that our body naturally makes. And it is going to act like a blocker, blocking the inhibitors from getting into the synaptic cleft. And because they're blocking the inhibitors, the dopamine is able to get into the dendritic receptor and stimulate it. So, okay, this is all before the heroin user takes any heroin. Now what's going to happen after they have ingested the heroin? Well, the thing that's going to happen is that now the heroin is going to act like a blocker at that inhibitor. It's going to block inhibitor release, and it is what's going to also allow the dopamine to continue to stimulate the dendritic receptor. Oh, I think I forgot to talk about what the effect of heroin is in general, right? So heroin is thought of as a depressant. Instead of being a stimulant, which causes a person to be active, heroin is a depressant that causes a calming, relaxing effect. You may notice that one other effect that is common amongst all these drugs is that this is also going to produce that euphoric effect. And it looks like one reason why the euphoric effect is going to come across because you've got that dopamine coming across again as well. Okay, so now let's talk about maybe a less commonly used drug, and that is 3,4-methylene dioxymethamphetamine, or how it's also known in the research community as MDMA. In the recreational drug using community, this drug is referred to as ecstasy. Sometimes it's called Special K or Molly. Right, and it's going to have the effect of some stimulating effects. Right, a person may use it when they go to a dance. They want to dance all night. So it's going to have the stimulating effect of allowing them to remain awake and exuberant all night long. But in addition to that, it's also going to have an effect where it causes the person to have an enhanced perceptual experience, right? Where they touch something and the thing that they touch feels really good. Or if they hug someone, the hug feels just awesome, right? And that's the reason why they're taking the drug, is the ecstasy is going to enhance whatever perceptions, whatever physical sensations they experience. Okay, so how does this drug work? To begin with, we've got a before situation, right? So before someone has taken ecstasy, the system that we want to be paying attention to is the serotonin reuptake system, right? So far, up to this drug, we'd been talking about drugs that affected the dopamine distribution. Beginning with ecstasy, we're now talking about drugs that are affecting serotonin distribution. But here what we're saying is that now you've got some neuron that's secreting serotonin into a synaptic cleft. The process that we're talking about is serotonin reuptake, where the serotonin has stimulated a dendritic receptor for some time, but then after it's done, that serotonin molecule will leave the receptor where it's at, and it will float into the terminal button that it came from, right? Hence, serotonin reuptake. This is what normally occurs before anyone has ingested any drugs. But then the user ingests ecstasy, they ingest the MDMA, and so the after effect is going to be that now the MDMA is going to mimic the serotonin, right? So this is basically the same thing as what would happen with the methamphetamines. So you have this serotonin molecule that's been stimulating a dendrite. It's supposed to be taken back up into the terminal button that it came from. But now this terminal button, because MDMA mimics serotonin, is filled with the MDMA and the serotonin. Put a little M there, M there, M there. Right, so it's getting filled up with both. Needs to kick something out. So what does it kick out? It kicks out the serotonin. And so the serotonin will then float across the synaptic cleft and continue to stimulate the serotonin dendrite that it had been stimulating before. Right, and that's what's leading to its effects. Okay, last drug that we want to talk about with all this is lysergic acid diethylamide, or LSD for short. To begin with, in describing this, we're saying that, again, we're talking about the serotonin system. What's going to happen though, right? So this time I don't have a before and after. We'll just say I've just got an after this time. But what we're saying here is that when someone ingests LSD, the LSD gets into a synaptic cleft and it has an affinity for serotonin receptors. So what's going to do is you've got this serotonin that's supposed to be getting into a synaptic cleft, and it's supposed to come over and stimulate these receptors. It's not, though, and the reason why the serotonin isn't going to stimulate those receptors is because this LSD that someone ingested got to the receptors first. Oh, I forgot to talk about what is the effect of LSD. Kind of an interesting drug. Doesn't necessarily produce like the stimulation, the exuberance, or the euphoria. Doesn't necessarily produce those kinds of feelings. Instead, what it's known for is its hallucinatory effects, right? So it's supposed to cause hallucinations. And of the hallucinations that are supposed to occur, there are basically two types. Either some type of visual hallucination or some type of auditory hallucination, right? You either see something that isn't there or you hear something that isn't there. Now, of the two types of hallucinations, really the one that is the most vibrant, at least in my experience, is the visual hallucination, right? Here, what's supposed to happen is as you're looking at something, it's supposed to like change shape. I'll just kind of give you a little anecdote of a time that I took LSD. And what happened was I was looking at a wall, and I was staring at the wall. I started to actually sense that the wall was moving back and forth, right? Back and forth in this slow, rhythmic pattern. And what I started to think under the effect of hallucination and the LSD was that the wall wasn't just moving back and forth, the wall was actually breathing, right? And so what I was watching was the inhalation, right? So the wall would expand, and then the exhalation of the air coming in and out of the wall. Right, and this all was because I thought the wall was moving. Why did I think the wall was moving? Because there was these LSD that was stimulating these dendritic receptors. Okay, that is everything that I've got for this lecture. So I'm going to go ahead and end it here. Thank you very much for your time, and I look forward to seeing you next week.